Let's welcome Amaury.
Yes.
Okay, I tried. With an unranking algorithm for the left parts of the 12-fold way that we'll hear more about. Over to you.
Good morning. In this talk, I will present some lexicographic unranking algorithm for each of the 12-fold way. So I will first introduce you to the 12-fold way. Then I will present some few properties of set partition in order to build a lexicographic unranking algorithm for set partition. Next, I will discuss about extension of our algorithm to the ordered set partition and to the Bell set partition. And finally, I will conclude. So the 12-fold way is a classification from the 60s due to AofA, which classifies function from a set of element n to a set of element k according to the nature of the function and if k and n are distinguishable or not. For instance, where when k is when the element of k is are indistinguishable and the element of k is, and we have interest on on injective function, we have the fifth k of the 12-fold way, which are a combination of n elements among k. So the counting formula for this object are well known. As you see, there is no empty case on the table. And in this talk, we will focus on a generation algorithm for this problem, and more particularly on unranking algorithm generation for this structure. So what's an unranking algorithm? An unranking algorithm is an unranking that giving a class of combinatorial objects C ordered, totally ordered by an order O, the user must be able to provide a rank of the structure that you want to generate, and the unranking algorithm will output the Earth structure, the Earth object of the class according to O. So intuitively, non-ranking algorithm is a bijection between this interval and the combinatorial class, and it has two main usages. The first one is we can adapt the algorithm in order to get exhaustive generator for free, or in order to get a random generator for free. One of the strong points of an unranking algorithm is that given a constructive enumeration formula for a combinatorial class, we can easily derive a non-ranking algorithm for this class. I will illustrate it on the example of combination with our counted by binomial coefficients. And how to build a combination? You have a set of n elements, and you need to choose k element among these n elements. So for each element, you will choose the first. You will ask yourself the following question: did I select this element in order to build my combination? If you select this element, it remains k-1 element to select among n-1 elements. That's the left part of the binomial coefficients. And if you don't select it, you have to select k element among n-1 element. That's the right part of the combination. So this combinatorial interpretation of binomial coefficient is straightforward to an unranking algorithm for combination. So the user will provide a rank, which is denoted by R here. And if R is less than this binomial coefficient, then we select the first element. Otherwise, we adapt the rank because we need to choose, we need to build in the combination, we don't have the first element, and build the combination recursively. So this is the output of the later algorithm. And as we can see, the combinations are sorted by lexicographic order, which is quite a natural order. But it's not the case for all the structure. For example, here you have the unranking algorithm derived from the interpretation of the scaling number of the second kind, and the order in which scaling number in which set partitions are sorted is seems really chaotic. So so in this talk, we are going to focus on if it's possible to have for each of the 12-fold way a lexicographic unranking algorithm for all the cases of the 12-fold way. The answer is yes, there exists a lexicographic unranking algorithm for each of the 12 cases, except for the problem related to set partition, which are the ordered set partition, the third case, the base set partition, which are the set case, the seventh case, and the set partition, which are the ninth case. So let's focus on this case. Set partition is a combinatorial structure. So I have a set of n elements, and I need to distribute it into a k block, such that each element of the set of n elements belong to exactly one block, and there is no empty block in my partition. It can give you as a Rota's problem like this. It's a surjective function from labeled set of elements to unlabeled set of elements. So here you have the two representations of set partitions. So some property about set partition. The set partitions are contained by a scaling number of the second kind, which are recursively defined like this. And in order to represent it, we will use the terminology of that Mansour introduced in 2012, which represents the partition as a sequence of blocks that are ordered by their minimal elements. So, for instance, 1, 2, 3, 4, 5 is the canonical form of this partition, and we then define the lexicographic order of a set partition, which is the intuitive order. Let's illustrate it by an example. So as you can see, here you have the set partition sorted by lexicographic order. And we can see that the 10th partition is greater than the 9th because 1, 2, 3 is greater than 1, 2. And the 19th partition is greater than the 18 because they have the same first block, but we have that the second block, which is 2, 3 for the 19th and 2 for the 18, we have that the second block of the 19 is greater than the second block of the 18. So let's focus now on lexicographic generation of set partitions. And in order to make an algorithm for this object, I define first the notion of a prefix of set partition, which is the first block of the first, which are the first elements of the first block of a set partition. So you have, for example, that 1, 1, 2, and 1, 3 are the prefixes of 1, 1, 2, 3, 4, 4, 5, 6. And when we have an interest on how many ways can we complete this prefix to maintain well-formed prefix, we have this formula, which given a prefix of len, L, which ending by D, will count how many ways can we complete this prefix while maintaining a well-formed prefix structure. So where does this structure come from? The first step is to count the way to the length of the elements that we can add to a prefix while maintaining a good prefix structure. So you can add from zero elements. In this case, the prefix that you give is the first block to n minus k minus l minus 1 plus 1. And this is because a block of a set partition can't have more than n minus k elements, because in this case, they will have an empty block. Once we have fixed the size of the elements that we want to add to our prefix, we need to choose the elements that we're going to add. This is denoted by u among n minus the last element of the prefix that we give. And once we have chosen the elements that we're going to add to the prefix, you have to build the other block of the set partition, which is contained by this scaling number of the second kind. So this formula has two other forms. So you have a form of this formula which has a less variable, which depend on less variable than the SNK formula, and you have the binomial transform of the formula, which is defined like this. One important thing to remark about this formula is that it is a summation over a different number of terms. So min n minus k and d here, and n min the n minus k n minus d here. This will have an importance later. So let's move on to the algorithm. In order to design our algorithm, we determine the partition by determining the block by block from the left to the right, and we determine the composition of the block element by element by iterating the STLNK formula, starting by the testing all the prefix by lexicographic order. Let's illustrate it. Let's illustrate it on an example. I want to unrank the 20th partition in 5 by 3 in 3 blocks. So for the initialization step, the user provides the rank 20, and the block that we want to build is empty, and we are going to test the first prefix in lexicographic order, which of len 1, which is 1. There is our formula gives that 25 partitions admit 1 as a prefix. We have that 20 is less than 25. So we add, 1 is a prefix of the desired block. So we add it in the block. We don't update the rank, and we check if 1 is the block, the first block of the partition. There is 6 partitions that admit 1 as a first block. So we update the rank. Here we set it to 20 minus 6, and we are going to test the prefix of that contain 2 elements, beginning by the first one, which is 1, 2. Our formula gives that there is 6 partitions that admit 1, 2 as a prefix. 14 is greater than 6, so we set the rank to 14 minus 6, which is 8. We don't update the block because 2 isn't a prefix of the desired partition. We test the next prefix of len 2, which is 1, 3. There is 5 partitions that admit 1, 3 as a prefix. Since 8 is greater than 5, the desired block is don't admit 1, 3 as a prefix. We test the next one, which is 1, 4. There is 4 partitions that admit 1, 4 as a prefix. 3 is less than 4. So 4 belong to the desired block, and we are going to check if 1, 4 is exactly the first block. There is three blocks which admit 1, 4 as a prefix. So 1, 4 is the block that we want to unrank. As a first optimization that we have done to our algorithm is to introduce a new formula which gives the number of partitions that admit at least this prefix. And this formula allows us to do binary search in order to determine the prefix instead to determine it one by one. So when we use binary search instead of linear search, we have this trace of execution of the algorithm. So instead of starting by 1, we start by 1, 3. There is 17 partitions that admit 1, 3 as a prefix. We update the rank, we don't update the block. We search the prefix 1, 4. We test if it's exactly 1, 4, and our algorithm converges in 3 steps instead of 5. As the next optimization that we have done, we use the several rating of RNK formula, which has different number of terms, and we select the rating that that necessitates the less number of terms in order to compute them. So let's move on implementation choice of our algorithm. So the main problem of our algorithm is to manage the Stirling number of the second kind. There are 2 main choices that we can do. So in order to compute them, we can memorize it by storing them in cache, for example. But Stirling number of the second kind are number of the order of n of n. And storing the entire Stirling matrix will be too expensive for when n is around 3000, until it will saturate the memory of our computer. The other choice that we can make is to use the explicit formula of Stirling number of the second kind, but it costs a linear time operation on on big integer, and in practice, it will be too expensive for n about 2000. So in order to bypass this problem, we made two remarks on our algorithm. In order to determine the case block of the algorithm of the partition, we only need two predetermined scaling column, which can be computed in linear time, and the main loop of our algorithm costs n log n time. So the computation of the column that we will need for the next block is cost less than the main loop. So we use parallel computation to provide the scaling number of the second kind. So here you have a representation of the algorithm. So you have the main thread, which will be initialized by providing the column, the scaling column. Then the main thread will split in two threads. The first one will compute the k-1 column that we will need to unrank the later partitions. And the other thread will compute the current block. The fact that we need less time to compute the k-1 column allow us to don't wait to make a recursive call here. So we can keep the efficiency, the time efficiency of precalculus with keeping the memory efficiency of explicit computation of the scaling number of the second kind. So here you have the theoretical complexity of our algorithm, and we benchmark algorithm provided 6 different implementations in order to obtain these curves. So the green one is a direct implementation of the binomial transform of our formula. The blue one is the direct implementation of RNK formula. The red one is the blue, the red and the orange one are the blue and the green one, in which we take in account the symmetry of binomial coefficients. And when we take the formula between the binomial transform and the direct implementation, which has the less term, we obtain the curves which are in brown and in purple. So the brown is when we pre-compute scaling number of the second kind, and the purple one is when we use parallel computation in order to determine scaling number of the second kind. So in this section, I will extend our algorithm to the ordered set partition and to the Bell set partitions. So the ordered set partition are contained by ordered number. So it's a set partition, but in which the order of blocks is taken in account. And one strong point, for this structure, we have that the prefix completion theorem that we made for set partitions still working on ordered set partition by just modifying scaling number of the second kind by ordered scaling number. So the same phenomenon happened in the case in the context of Bell set partition, which are set partition which variable number of blocks, in which in the prefix completion theorem we replace scaling number of the second kind by Bell number of the second kind. So as a conclusion, in this talk, we present a prefix completion theorem that allow us to generate set partition in lexicographic order using unranking algorithm. One strong point of our algorithm is that our algorithm is easily adaptable to other structure by modifying few lines of code. And this leads straightforward to the first future work that we want to do. We want to generalize our algorithm in order to don't have to modify this few line of code. And we want to improve the efficiency of other existing algorithms using concurrency, as we do to save memory and without degrading time complexity. This work led to Go library, which is available on this URL. And as a final remark, we have now lexicographic and ranking algorithm for each of the 12-fold way. Thank you for your attention.
Questions?
Hello. One of the uses of unranking algorithms is for random generation, especially if you want to produce distinct objects. But then the lexicographical order is maybe not a must. Have you considered using different orders? Could they help in the unranking algorithms? I know that it helps to switch to a different order when you are looking for unranking algorithms for unmissable combinatorial classes, like in the framework that Flageolet defined. You can, in the same way you can count, enumerate from the specifications, you can unrank from the unmissable specifications. I know that is if you, instead of using lexicographical order, you unrank by another kind of order that's called boustrophedonic order. You can improve the complexity of the algorithms. And I'm wondering if this could be used also in this context.
The real difficulty of work was to lexicographic order because it will be more efficient to generate it by using the interpretation of scaling number of the second kind. So we encode it, and it's several times more efficient to generate in this order, the order induced by combinatorial interpretation of scaling number of the second kind than in lexicographic order.
Oh.
Did I answer your question?
No. One is allowed to ask questions in the back of the room. I'm happy to.
If you want to do some sport, we can alternate. So there is this old book by Niran Wills and Wilf on ranking and unranking. And at the beginning, you show this table where only your 3 cases were not yet done. All the other cases, they were covered by Niran Wills and Wilf or by a set of other authors where it was done for the other ones.
You asked me for the references of the other algorithm.
Mm-hmm.
You can find let me put the table. You can find the most of them by in the preprint of Rusky.
Ah, okay.
On the Rusky. And there are some cases which are easy. For instance, the n sequence in K, which are just Euclidean division.
And in the volume 4 of GNUS, there is a lot on generate all possibilities and so on. So yes. I won't be astonished that perhaps he revisited some of those ones with respect to the old work of the people that you were mentioning. And did you consider also not just ranking and unranking, but possibly what could be the cost if you want to do random generation? For sure, if you have ranking and unranking, you have a random generation just by generating the number. But if you compare with other approaches, you went a little bit to this direction or not?
I think using algorithm generation instead of random generation will not mean a significantly loss of efficiency. I think we have the same efficiency as we.
The same efficiency.
Yes.
Questions? And I'll ask a quick one. Suppose you're generating the objects one after the other. Can your algorithm profit from that? So you're enumerating the algorithms in the nice lexicographic order, but you use your unranking algorithm. Maybe you can take advantage of that special case.
One after the other, I don't think it will be worth it because there exist several algorithms that are built like an initialization step and a function step which will compute the next object. So I think the exhaustive generation is if we make such algorithm with an initialization step and a step function, which means more efficient than generating when putting the unranking algorithm into a loop.
Okay.
You can get constant amortized time
Mm.
every step.
Well, in the theme of having one algorithm that works for every use case, that would have been nice to just adapt the existing. More questions? Then let's go for coffee.